Okay, babies, as promised in the last video, I told you we would interpret some stuff. So we're going to do that from this computer output that I used in the last example, or in the computer output video, I should say. All right, so let's look at this. Let's see if we can interpret the slope, interpret the y-intercept, the correlation, the coefficient of determination. Let's see if we can do all of that. I already talked to you about interpreting the plots that are given. I went over the idea that the scatter plot was nice and linear, the residual was nice and scattered. So we did talk about that in the last video. So let's look at interpreting our slope. Our slope for this particular LSRL, the slope equals 0.740767. Now, as you can see from this, it is positive, and that makes sense given what your scatter plot looks like. So how am I going to interpret it? Well, I would interpret it this way, and you don't necessarily have to use my wording for this, but if you want to, it'll help you keep it straight in your head. All right, so I can predict an increase of 0.740767 degrees in Buffalo temperatures as Bismarck temperatures increase by 1 degree. Okay, another way to write it. For every additional degree increase for Bismarck temperature, I can expect an increase of about 0.740767 degrees in Buffalo temperatures. Okay, and I know my handwriting's sloppy, and I'm sorry. Okay, so let's look at these. I can predict an increase of 0.740767 degrees in Buffalo temperatures as Bismarck temperatures increase by 1 degree. So in other words, y is responding to x. That's how you're going to talk about the slope. For each additional degree increase for Bismarck temperature, I can expect an increase of about 0.740767 degrees in Buffalo temperatures. So this is how I'm going to interpret the slope. There's your slope right there. Okay, let's use a different color for my y-intercept. Okay, y-intercept. Let's look at our y-intercept. It is 23.5915. Okay, so my y-intercept, I just looked at that and I've already forgotten it. How embarrassing. Okay, so there's my y-intercept. What does that mean? Well, that means that I can predict a temperature of 23.5915 degrees in Buffalo when the temperature in Bismarck is 0 degrees, okay? Because x, when x is 0, we have our y-intercept, so Bismarck is my explanatory variable. So that's how I would do that. Okay, correlation. What is correlation going to look like? All right, what color we won't use now? Okay, so correlation. The correlation coefficient is 0.995. It's R. What does this mean? It means there is a strong, it's close to 1, positive, my slope is positive, okay? There's a strong positive, and I've looked at my scatter plot, linear relationship. You can also use association right here. Between Bismarck, sorry kids, had a brain fart there for a minute. And if you'll notice this, this is almost your SUDS. This almost takes complete care of describing the distribution altogether, because I've got my direction here, my sign, and my type of graph here. So keep that in mind. So interpreting R is kind of like interpreting the whole thing. Okay, now we're going to look at the coefficient of determination, R squared. Purple. R squared is 0.99. What does that mean? 99% of the variability in Buffalo temperature, yes, that always has to be your response variable, can be explained by this linear model. Another way to think about that is the variability or the variation in temperature in Buffalo. 99% of that can be attributed to whatever's happening in in Bismarck, sorry, because Bismarck is my explanatory variable. Isn't that cool? I knew you'd love it.